Next up, what I want to talk about is the concept of continuity. This is still section 1.2, and let's talk a little bit about what continuity means by drawing a graph. Continuity just means that a function is connected from the beginning to the end, so you can draw the whole thing without lifting your hand. That's what it means to be continuous. So, on the xy plane, we like graphs that are always connected. We can do a lot of good, useful mathematics with those graphs that are always connected. Now, in the next few seconds, I'm going to show you how to find whether a function is connected at a certain point called A. So how do we know if the function is connected at that location? So how do you know that we can graph the line without lifting our hand right above the number A? So there's a few things that we have to check. First of all, we have to check that there's a solid point right there at that location. We call that the f of A. We want to investigate that the f of A actually exists. So in other terms, we want to check that there's a solid point right there, not a hollow point. Because if you have a hollow point, that means the graph does not exist there, and so we cannot graph it all without lifting our hand. That's what that little open circle means. So hopefully there's a closed circle on our graph like it is in this case. So that's the first step. Make sure that there's a closed circle. Next, what we want to do is make sure that the limit before and the limit after are the same amount. So we want to make sure that the bridge on the left and the bridge on the right don't point in different direction, because if they point a different direction, then obviously I cannot graph the whole thing without lifting my hand. I would like my graph from the left and from the right to meet in the same spot. And then since I have a solid point right there in the middle, I'll be able to traverse and graph the whole thing without lifting my hand. Now, those are called the limit as x approaches A from the left and from the right. So this one is called the limit as x approaches A minus on this function f of x. And this blue one is called the limit as x approaches A from the right side, so A plus, on this f of x. So for the problem to be continuous at the point A, those three numbers should all match. This one, this one, and this one should all be the same. If one of them is different, then you're going to have a problem that is not continuous. So like for example, if the middle one is different, then your graph will look like this. The bridge on the left and the bridge on the right meet in the same spot, but the solid point is somewhere else. So again, there's no way on earth I can graph that whole thing without lifting my hand off the paper. Or there are situations where the bridge on the left connects with the solid dot, but the bridge on the right is off. In which case, what does that mean? That means that this third one is not matching with the other two. So when all three of them match, that's great, because that will tell us that the function f of x is continuous at the point A. So in a few minutes, I'm going to give you some examples, and what we're going to be doing is checking whether the function is continuous at the point A or not. So in step number 1, what we're going to do is investigate how much is the function when we plug in A into the function. Is that even going to have an answer or not? So in other terms, is there a black solid point right there at that location where x is equal to A? Step number 2 is going to be to investigate the limit as x approaches A on this function f of x. And notice how I put A, not A plus or A minus. This notation right here means that you need to check both of them. Since I'm not putting a plus or minus, that means you gotta do both sides, left and right. And hopefully, those two numbers on top and on the bottom are the same. Typically speaking, we call that number capital L. If they're both capital L, then we can say in step number 3 that the function is continuous. If f of A is equal to the limit as x approaches A on this function f of x, then they'll both be equal to L, and we say that the function is continuous. So f of x is continuous. So that's what we're going to be doing in the next few minutes. So this is the theorem that I was just mentioning, or the definition if you want. So again, first check that the function exists, then check if the limit exists, then check that the numbers on the first step and the second step were the same. If they are, then great, that means you have continuity. So let's do example number 8, which says the function f of x is x squared minus 5, and they want us to check if the function is continuous at 3. So this is kind of like the A of the problem if you want. Okay, so let's see. First, step number 1. What I do in step number 1, I check f of the number that they want. In this case, the number that they want is the number 3. So I'm going to check what is f of 3 equal to. Does it even exist? That means take the function that you have and plug in 3 into all of the x's. And when you do that, you get 9 minus 5, which is at the end 4. So the function actually exists at the number 3. There's an answer, and the answer is 4. So that's great. So that's the end of step number 1. Step number 2 says check the limit as x approaches to 3 on this function f of x. So first of all, how much is f of x even in the first place? Well, it is x squared minus 5. So let's go ahead and write it down. So x squared minus 5 is the function f of x. So we're going to plug it in because that's what it really is. And at this point, we have a limit. So before I separate left limit by itself and right limit by itself, let's see if I can plug the number in, right? So the 3, can it be plugged in? Does it work, or does it give me an indeterminate form? Well, if I plug it in, I get 3 squared minus 5, which is 9 minus 5, which is at the end 4. So all I did here is notice that it's a limit, replace x with 3, then evaluated the numbers. So step number 2 is done. I didn't have to do left limit, right limit. I was able to do both of them in one shot. Step number 3 is to check, is the first answer that you got equal to the second answer that you got? Is it true or not? The answer is definitely, right? We got 4 for the first one, we got 4 for the second one. They are both equal to 4. So that's amazing. That's awesome, because that means that the function is continuous. So in this case, we can say f of x, which is the x squared minus 5, is continuous at x equal to 3, the number that we had in question. So what does this mean? This means the following. If you graph the function and look at where 3 is, you'll notice that the function x squared minus 5 has 3 things going on for it. First, at 3 itself, there's a solid point. Next, the bridge on the left and the bridge on the right are pointing in the same direction, so that way I can graph the whole thing without having to lift my hand above 3. That's what this means.